Hi all, in this video we can see what is the different methods to generate excess carriers in a semiconductors and what are the different methods for recombination of this excess carriers. So what I mean by this excess carriers means the charge carriers in semiconductors which are in excess of their thermal equilibrium value are called excess carriers. So we know that at thermal equilibrium we have electron hole pairs generations are there. Similarly, electron hole pair recombinations are there. In addition to this generation of electron hole pairs due to thermal energy, we are using any extra energy to generate excess carriers, and that generated carriers is called as excess carriers. So this excess carriers are the carriers in semiconductor which are in excess of their thermal equilibrium values. So at thermal equilibrium there should be electron hole pairs are there. In addition to this electron hole pair, if we are using any source of energy other than temperature, then the generated electron hole pairs are called excess charge carriers. So why we are generating this means most semiconductor devices operate by the creation of charge carriers in excess of the thermal equilibrium value. So most of the semiconductors are operated by the use of this excess charge carriers rather than this thermal equilibrium charge carriers values. So that's why we are going for this excess carrier generation. We have different methods for this excess carrier generation. We have optical excitation, injection of electrons, electron bombardment, etc. Different methods are there for this excess carrier generation. So before going to this excess carrier generation in detail, we need to understand two terms, that is low level injection and high level injection. So the low level injection means we already said that we are generating the excess carriers due to excess carriers using any other form of energy other than temperature. So we have charge carriers are there for this temperature, and if you are comparing the charge carriers equilibrium majority carrier concentration with the excess carrier concentration, then if the excess carrier concentration is small compared to this equilibrium majority carrier concentration, then we can say it as low level injection. So we injected the excess carrier in a semiconductor, that injected carriers amount or concentration is small compared to the thermally generated majority carrier concentration, then we can say it as low level injection. Then what do you mean by high level injection? High level injection is nothing but if the injected excess carrier concentration is large compared to the equilibrium majority carrier concentration, then we can say it as high level injection. So at thermal equilibrium there should be some charge carriers are there. In addition to this charge carriers, we are increasing the concentration of electrons and holes due to any other form of energy, and that generated carriers is called as excess carriers, and this excess carrier concentration is large compared to the equilibrium majority carrier concentration, then we can say it as high level injection. So next we can see what are the different methods for this excess carrier generation and recombination. So basically we have two methods. One is direct generation and recombination. Second one is indirect generation and recombination. So we can see different methods here. So first we are going for this direct generation. First we are going for the generation methods, after that we are going for this recombination methods. So first method is the photo generation. So the name itself, it is using light energy. So this is the process of generating excess carriers by shining light on semiconductor. So we are using optical energy or any source of light to generate excess carriers other than the thermal equilibrium majority carrier concentration. So you should remember that the excess carriers are generated using any form of energy other than temperature, and if the energy used is source of light or optical energy, then we can call it as photo generation. Then how this electron hole pairs are created using this photon or light means, if a photon of energy greater than band gap of semiconductor falls on it, then the energy of photon is absorbed by electron in the valence band and is excited to the conduction band. So if a photon of energy greater than the band gap energy of semiconductor falls on it, then that energy will be captured by an electron in the valence band. They are already in covalent bond, so due to this energy that bond will break and that electron will move to the conduction band. So that electron become free to move and that will be excited to the conduction band. So that result in a generation of electron hole pairs. So the optically generated electron and holes are equal. So we can say that optically generated holes and electrons are equal. Why means if a photon of energy greater than the band gap energy is eliminated to a semiconductor, the electron in the valence band will accept that energy and that will excited to the conduction band. So due to this excitation, there is a vacancy created at the valence band that is called holes, and this holes will create a free electrons. So we have one electron and one hole. So every time the optically generated holes and electrons are equal. So that carrier concentration should be excess than the thermal equilibrium concentration. So that's the way the photo generation happens. So photo generation means we are generating the excess charge carriers by shining light. So if a photon of energy greater than band gap energy is eliminated to a semiconductor, the electron in the valence band that will accept that energy and they will excite. Due to this energy, the electron will break the covalent bond and they will excited to the conduction band. So if there is a vacancy created at the valence band, that is called holes, and that free electron move to the conduction band. So that is called photo generation or optical generation. So what is the total number of electrons now in the crystal means the electrons due to this optical, the electron generated due to this optical energy plus the already generated electron due to temperature. So we can say that the total electron concentration N equal to the equilibrium electron concentration N0 plus the excess electron concentration due to this optical energy del N. Similarly, the total hole concentration P is equal to the equilibrium hole concentration P0 plus the excess hole concentration del P. And remember that this del N is equal to del P, that means excess electron generated due to this optical energy is equal to excess hole generated. That is called photo generation. Next we can see how this what is the nature if a photon is incident on a semiconductor. So for that we are taking a light of intensity I0 falls on one face of sample of thickness T. So we are taking a semiconductor having thickness T and we are illuminating that semiconductor with a light of intensity I0. Then the amount of light transmitted through that semiconductor is I of t equal to I0 e raised to minus alpha t. So in that I0 amount, a fraction of energy will lost and the remaining is transmitted as I of t equal to I0 e raised to minus alpha t, where alpha is the absorption coefficient. So we can see in figure 1. So we have a sample having thickness T, a semiconductor specimen having thickness T. So there is an I0 amount of energy is incident on that semiconductor. From that I of t amount is transmitted out. So remaining energy is absorbed in that crystal. So that's called this equation is I of t equal to I0 into e raised to minus alpha t, where alpha is the absorption coefficient. And in second figure we can see the absorption coefficient as a function of energy of photon. So in this figure we can see that this absorption coefficient is depend upon the material, the absorption coefficient of a material depend upon the incident wavelength or energy of the photon. That means if an incident photon have a energy greater than the band gap energy, then the velocity of the excited electron will be higher than the thermal velocity. That means under thermal equilibrium, the electron have a velocity that is called mean thermal velocity. So if we eliminated a crystal with light source, so if the light source energy is greater than the band gap energy, the electron will accept that energy, and the valence band electron will accept that energy, and they move to the conduction band. So that time the excited electron's velocity will be higher than the mean thermal velocity of electrons. So after a particular time, what will happen means this excited electron will lose their energy and come back to the valence band itself and combine with the holes, and then they neutralize. That means recombination may happen. So the excess of energy in that time released in the form of heat during different scattering events until its velocity becomes equals to the mean thermal velocity. So if an electron get an energy greater than the band gap energy, the valence band electron break their covalent bond and they will move to the conduction band. So after a particular time, the free electrons in the conduction band lose the conduction band, come back to the valence band itself and emitted that excess energy in the form of heat or light. So if it is a photon, then it's emit in the form of light. If it is direct band gap semiconductor, then that energy is emitted in the form of light, and if it is indirect band gap semiconductor, the energy is emitted in the form of heat. So that excess energy is emitted in the form of heat, and then and then their velocity becomes the thermal velocity at that temperature. So that's we can say that when an electron get an energy greater than when a photon incident on a semiconductor having energy greater than the band gap energy, then the electron in the valence band will accept that energy, will get that energy, and they will move towards the conduction band, and after some time this conduction band electrons may come back to the valence band itself, and they emit the energy in the form of heat. So at that time, after so many scattering, the excess velocities come back to the mean thermal velocity at that temperature. And we can say that the conductivity due to this excess carriers generated due to this photo energy or this optical energy is called photoconductivity. So due to this photo generation, the excess carriers are generated and thus the conductivity increased, and that conductivity is called photoconductivity. And we have the expression for that photoconductivity as sigma OP is equal to Q NOP. That means excess carriers generated due to optical energy into mu n is the mobility, and Q is the charge of electron, plus Q POP mu P. Q POP means the excess holes generated, and mu P is the mobility of holes. Or we can say that the excess carrier generated is represented as del N and del P. So we can say that sigma OP equal to Q del N mu N plus Q del P mu P. So the derivation of this conductivity we can see later. So now just remember that the conductivity sigma OP equal to Q del N mu N plus Q del P mu P. So in this figure we can see that the photo excitation and radiative recombination. So we already said that when a semiconductor get an energy when a semiconductor is illuminated with a optical energy, that is photon energy greater than the band gap energy, then that electron in the valence band will get that energy and they will excited to the conduction band. So we can see that here the band gap is the EC minus EV is 1.43 electron volt, and we have a photon of energy 2 electron volt. So we can see that this 2 electron volt is greater than 1.43. That means the photon energy is greater than the band gap energy. So due to this higher energy, the valence band get more energy to break the covalent bond, and they will move to the electron become free to move to the conduction band after, and they will occupy top of the conduction band. So after some time they will come back to the bottom of conduction band. Then from that they will come back to the valence band itself. So at that time they will emit the energy in the form of photons. So they will after coming back, the electron will recombine with the holes and they will neutralize. So at the time of excitation, a vacancy is created at the valence band, and at the time of recombination, that will disappear. So the electron and holes will neutralized. So this is the way the photo generation and photo recombination happen in semiconductors. So next we can see what is the expression for this carrier generation due to this optical energy. So we know that under thermal equilibrium the generation rate is balanced by recombination rate. That means somewhere generation can happen in the crystal, some other place the recombination will happen. So the equilibrium concentration of this electrons and holes under thermal equilibrium is represented as N0 and P0, and we know that the generation rate is always proportional to the carrier concentration. So under thermal equilibrium the generation rate is always proportional to N0 P0, or we can say that G of t equal to alpha N0 P0, or we can say it as alpha Ni square. So if we are considering the optical generation, then that can be represented, this optical generation rate can be represented as GOP. So in addition to this thermal equilibrium, we have optical energy is also there. So the optical generation rate is represented as GOP. So this GOP we know that now in the if we are considering the semiconductor, we have thermal equilibrium carriers are there, as well as the excess carriers are there due to this optical energy. So in that case also there should be a balance between generation and recombination. So we can write this now, this generation rate, the total generation rate, that means generation due to thermal energy plus the generation due to optical energy, that is GT and G plus GOP equal to alpha NP, where N is the total number of electrons now in the crystal and P is the total number of holes now in the crystal due to this thermal equilibrium as well as this optical energy. So we can say that G of T plus G of OP equal to alpha NP. We can replace N and P. N is N0 plus del N and P is P0 plus del P. And we know one more thing, in optical generation the generator holes should be equal to electrons. So we can say that del N equal to del P. So in that equation we can replace del P as del N itself. So you will get alpha N0 plus del N into P0 plus del N. Next you expand the bracket. So after expansion you will get this GT plus GOP equal to alpha N0 P0 plus alpha times N0 plus P0 del N plus del square N. So we here considering the low level injection, so we can neglect the term del square N. So we can say that and one more thing, this alpha N0 P0 is already represented as GT. So we can replace this alpha N0 P0 as GT. So left hand side and right hand side we have GT. So that term cancels. So remaining is GOP is equal to alpha times N0 plus P0 into del N. Del square N term also neglected. So that represented as del N by tau N. Where tau N is 1 by alpha times N0 plus P0. So from this equation we can write del N equal to del P equal to GOP into tau N. So what means this excess carrier concentration, that is del N equal to del P, should be equal to the excess carrier rate, that is GOP into minority carrier lifetime, that is toy. So the lifetime means minority carrier lifetime means after that the electron hole will recombine. After that time the electron hole will recombine. So remember, the excess carriers generated due to this optical energy should be equal to the optical generation rate into minority carrier lifetime. Del n equal to del p equal to GOP tau n, where tau n is 1 by alpha times n0 plus p0. So that's all about photo generation. So we can summarize the photo generation as, if a photon of energy greater than the band gap energy is illuminated to a semiconductor, the electron in the valence band electron will get that energy and they will excited to the conduction band, and that's a free electron will be generated at the conduction band, as well as a hole will generated at the valence band. So this is called photo generation, and always this excited electron will occupy top of the conduction band. After some time the energy after releasing this energy, after so many scattering, the energy is released and they will come back to the valence band, and they will recombine with the holes and neutralize. So that is called photo recombination. So next we need to see what are the different recombination methods. So next video we can see different recombination methods.